Now we turn to the operations. This is where we meet the rotations that keep an AVL tree balanced. Every AVL imbalance is fixed by one of four cases. We name each case by the shape of the heavy path, which runs from the imbalanced node down to the key you just inserted. Let's read the four cases. The LL case. The left child's left subtree is heavy. The heavy path leans the same way twice. We fix it with a single right rotation at the imbalanced node. The RR case is the same as LL but with left and right swapped. The right child's right subtree is heavy. We fix it with a single left rotation. The LR case. The left child's right subtree is heavy, so the heavy path bends into a zigzag. This one needs two rotations. First a left rotation at the child, then a right rotation at the node. The RL case is the same as LR but flipped left to right. The right child's left subtree is heavy. We fix it with a right rotation at the child, then a left rotation at the node. All four rotations are pure pointer work. There is no clever logic beyond reattaching three links in the right order. So on these slides we show the before and after picture and the C code and skip the pseudocode. You may think you can grab any node and hang it on the short side to even out the heights, but a rotation is not a free reshuffle. It is a fixed relink of one parent, child, and grandchild that keeps left less than node less than right true everywhere. Break the order and search stops working. Let's start with the LL case. We insert 10 under 20 under 30. Node 30's balance factor drifts to +2, so it is now imbalanced. A single right rotation at 30 fixes it. The left figure shows the tree before the fix. 30 sits at the top with balance factor +2. 20 hangs below it on the left. 10 hangs below 20, again on the left. This is a straight left-left line. The right figure shows the tree after we rotate right at 30. 20, the middle key, becomes the new root of this subtree. 10 stays as its left child. 30 drops down and becomes 20's right child. Every balance factor is back to 0. So the middle key 20 rises to the top and 30 drops to the right. The order still holds. 10 is less than 20 and 20 is less than 30. The RR case is the LL case with left and right swapped. We insert 30 under 20 under 10. Node 10's balance factor drifts to -2. A single left rotation at 10 fixes it. The left figure shows the tree before the fix. 10 sits at the top with balance factor -2. 20 hangs below it on the right. 30 hangs below 20, again on the right. This is a straight right line. The right figure shows the tree after we rotate left at 10. 20, the middle key, becomes the new root. 10 drops down and becomes its left child. 30 stays as its right child. Every balance factor is back to 0. Notice the final shape is the same as the LL case, just reach from the other side. The two rotations match in the same way. Rotate left is rotate right with left and right swapped in the C code. The LR case is a zigzag. We insert 20 under 10 under 30, but this time 20 becomes 10's right child, not its left child. So the heavy path bends. One rotation at 30 will not fix this. It needs two rotations. The left figure shows the tree before the fix. 30 sits at the top with balance factor +2. 10 is its left child. But 20 hangs off 10's right side. That bend from left then right is the zigzag. The right figure shows the result of two rotations. First we rotate left at 10, which straightens the zigzag into a plain left-left line. Then we rotate right at 30, the same fix as the LL case. 20 ends up at the top, with 10 on its left and 30 on its right. So the idea is two single rotations, one after the other. First rotate the child to straighten the line, then rotate the node, exactly like LL. Together these two steps make up the double rotation. You may think one rotation at 30 fixes any balance factor of +2, but on this zigzag it does not. A single right rotation just tips the imbalance to the other side. The warning sign is the child leaning the opposite way from the node. Here 10 leans -1 while 30 leans +2. That mismatch means you need the child rotation first. The RL case is the same as the LR case but flipped left to right. We insert 20 under 30 under 10, and 20 becomes 30's left child. It is a zigzag again, just on the other side. The left figure shows the tree before the fix. 10 sits at the top with balance factor -2. 30 is its right child, but 20 hangs off 30's left side. That bend from right then left is the zigzag. The right figure shows the result of 2 rotations. First we rotate right at 30, which straightens the zigzag. Then we rotate left at 10, the same fix as the RR case. 20 ends up at the top, with 10 on its left and 30 on its right. Now try one yourself. A node X has balance factor +2. Its left child has balance factor +1, so the child is heavy on its own left. Which single rotation fixes X, and why is it not a double rotation? Decide before you advance. The answer is a single right rotation at X. The heavy path is a straight left-left line, not a zigzag, so we do not need a child rotation first. A double rotation is only for the LR and RL cases, when the child leans the opposite way from the node. This is rotate right in C. It takes one node called Y, the node that is out of balance, and it returns the new root of that subtree. First we grab Y's left child and call it X. This X is the node that will rise to the top. Then we save X arrow right in a helper called T2. This is the subtree that needs a new home after the rotation. Now the first relink. We set X arrow right to Y so Y becomes X's right child. The second relink. We set Y arrow left to T2, so Y adopts X's old right subtree as its new left subtree. Now we fix the heights. We update Y first, because after the swap Y sits lower in the tree. Its new height is 1 plus the max of its two children's heights. Then we update X's height the same way, 1 plus the max of its children's heights. Because Y is already correct, X now reads good values. Finally we return X, the new root of this subtree. The order of the height updates matters. Update Y before X after the swap Y sits lower, so its height must be computed first. Otherwise X reads an old value. The cost of each rotation is big, O of 1. It is 3 pointer rights and 2 height updates, no matter how big the subtrees are. Rotate left is rotate right with left and right swapped. Let's put it all together as pseudocode. AVL insert is just the binary search tree insert from chapter 10, plus a height update and a rotation check on the way back up. It starts like a normal insert. If X is nil, we reached an empty spot, so we create a new node and return it. If the key is smaller, we go left. If it is larger, we go right. If it is equal, it is a duplicate, so we change nothing. After the recursive call returns, we do the AVL work. We update X.height to 1 plus the max of its two children's heights. Then we compute the balance factor as the left height minus the right height. Then 4 checks pick the rotation. If the balance factor is greater than 1 and the key went left of the left child, that is LL, so rotate right. If it is less than -1 and the key went right of the right child, that is RR, so rotate left. The other two mixed cases are LR and RL, each a double rotation. If none fire, X is already balanced. The trick is comparing the inserted key to X.left.key or X.right.key. That one comparison tells LL apart from LR, and RR apart from RL. It says which side of the heavy child the new key landed on. Let's trace an AVL insert one step at a time. We insert 3 keys in order, 30, then 20, then 10. Before you advance, try to predict it. Which insert first pushes a balance factor to plus or minus 2, and is it the left-left case, or one of the others? We start with 30. It is the very first node. Its height is 0, and it is balanced all by itself. Now we insert 20. 20 is smaller than 30, so it becomes 30's left child. The balance factor of 30 is now plus 1. That is still inside the allowed range of -1 to +1. Now we insert 10. 10 is smaller than 20, so it becomes 20's left child. We walk back up. The balance factor of 20 is 0, which is fine, but the balance factor of 30 is now plus 2. That breaks the rule. This is the left-left case. So we fix it with one rotation. We rotate right on 30. Now 20 becomes the new root of this little subtree. 10 is its left child and 30 is its right child. Every balance factor is back to 0, and the tree is balanced again. This is the same insert. Now in C the function is called AVL insert. It takes a node and a key, and it returns the new root of this subtree. First the base case. If the node is null, we reached an empty spot, so we make a new leaf node with this key and return it. If the key is smaller than node arrow key, we go left. We call AVL insert on the left child, and we store the result back into node arrow left. If the key is larger, we go right the same way, and store the result back into node arrow right. If the key is equal, it is already in the tree. We just return the node with no change. After the recursion comes back, we update this node's height. It is 1 plus the taller of its 2 children's heights. Then we compute the balance factor of this node. That is the left height minus the right height. Now the 4 checks. If the balance factor is greater than 1 and the key went into the left child's left side, that is the left-left case. We rotate right. If the balance factor is less than -1 and the key went into the right child's right side, that is the right case. We rotate left. If the balance factor is greater than 1 but the key went to the right of the left child, that is the left-right case. We first rotate left on the left child, then rotate right on this node. The last case is the same idea, flipped to the other side. The balance factor is less than -1, and the key went to the left of the right child. That is right-left. We rotate right on the right child, then rotate left on this node. If none of the 4 checks fired, the node is already balanced, so we just return it unchanged. The whole insert is big. O of log n, the walk down is proportional to the height, and the balance rule keeps the height at big O of log n at most 1 rotation fires per insert. Let's look at AVL insert at 3 levels of detail: the plain concept, the pseudocode, and the real C. In plain words, insert like a normal binary search tree. Then walk back up and recompute each ancestor's height. If a balance factor leaves the set -1, 0, +1, do 1 rotation to fix it and stop. In pseudocode, that is 3 lines. Set the height to 1 plus the max of the 2 children. Compute the balance factor as left height minus right height. Then, if the balance factor is greater than 1, return rotate right. The C code says exactly the same thing. Node arrow height gets 1 plus max int BF gets balance factor of node. And if BF is greater than 1, return rotate right of node. The key point: only 1 rotation ever fires per insert, even though the recursion walks through every ancestor. Fixing the lowest broken node fixes all of them. That is why AVL insert is big. O of log n, not big. O of log squared n. Now the same fix, but deeper inside a bigger tree. We build a tree with 8 keys. Then we insert the key one. That causes a left-left imbalance at node 10, which sits 3 levels down from the root. The left figure shows the tree right after we insert one, before any rotation. Node 10 now has a balance factor of +2. Its left side grew too tall. The right figure shows the tree after the rotation. We rotate right at node 10. 5 moves up into 10's old place, and 10 becomes the right child of 5. Node 10 is back to balance factor 0. Notice the rotation only touches the broken node's own subtree, 10, 5, and the new one. The other side of the tree, rooted at 30, is not touched at all. A rotation is a local repair. AVL delete follows the same idea as insert. You do a normal binary search tree delete, then rebalance as you unwind. We do not implement it in this course, but let's see how it is different. First difference: a delete can need rebalancing at every ancestor on the path, not just one node. With insert, one rotation always fixes everything. With delete, it may not. Second, the two-child case still uses Chapter 10's trick first. You replace the node with its in-order successor. Only then does the rebalancing walk begin. Third, the building blocks are the same. Rotate left and rotate right do not change at all. We stop here on purpose. Insert already teaches balance factors, all 4 rotations, and the update height while unwinding pattern. Delete just adds bookkeeping, not a new idea. Now red-black trees, again just for comparison. A red-black tree relaxes AVL's strict height rule into a coloring rule. Every node is red or black. A red node's children are both black, and every path from the root down to a null leaf crosses the same number of black nodes. Because the balance rule is looser than AVL, you get fewer rotations on insert and delete. It still guarantees the height stays at most 2 times log of n plus 1, so it is still big O of log n for everything. This is why real libraries use it. The C++ standard map, Java's tree map, and the Linux scheduler are often built with red-black trees. Write-heavy code likes fewer rotations. In the picture, the dark nodes are black and the red nodes are red. Every path from the root to a null leaf here crosses the same count of black nodes. One warning: you may think red-black is just AVL with colors equally balanced, but it is only roughly balanced. It lets one path be up to twice as long as another. That looser rule is the whole point: fewer rotations per write in exchange for a slightly taller tree. Now B-trees and B+ trees, again for comparison. A B-tree node is different. It holds many keys and many children, not just one key and 2 children. This high fanout keeps the tree very shallow. B-trees are built for disk and database storage. One node maps to one disk page. Fewer levels means fewer expensive disk reads for each lookup. A B+ tree keeps all the data in the leaf nodes and links the leaves together side to side. That makes range scans fast. This is the layout most database indexes really use. The picture shows one B-tree node with 2 keys, 17 and 35, and 3 child pointers. Each child is itself a node holding several keys. Notice we drew this as boxes, not as a pointer diagram. A B-tree node is a structure you compare and read, not a chain you walk one link at a time. Let's put all 3 side by side. The 3 columns are AVL, red, black, and B-tree. First, the balance rule. AVL is strict. The balance factor must stay within 1. Red-black uses colors and black height, which is looser. A B-tree keeps every node at least half full. Second, the height. AVL is the tightest. About 1.44 times log n. Red-black is about 2 times log n. A B-tree is log base m of n, which is very shallow. Third, rotations per update. AVL insert does at most 1, but delete may do 1 per ancestor. Red-black does at most 2, plus some recoloring. A B tree uses node splits and merges instead of rotations. Fourth, what each one is best for. AVL for read-heavy work in memory. Red-black for write-heavy work in memory, which is why the standard libraries use it. A B tree the moment the data lives on disk. A quick way to choose. Use AVL when reads dominate and you want the shallowest tree. Use red-black when writes dominate and you want fewer rotations. Use a B tree the moment a node might live on disk instead of in memory. A quick check. A database index holds 1 billion keys on disk. Both a B tree and an AVL tree are big. O of log n, so why does the B tree win here? Think about it before the answer. The answer is the base of the logarithm. An AVL tree's height grows with log base 2 of n for 1 billion keys. That is about 30 disk reads. A B tree with hundreds of keys per node grows with log base m of n for a large M. That is only 3 or 4 disk reads. Fewer levels means fewer slow disk seeks.